Okay, so our next speaker is Beatriz Villarroel. She's an astronomer at the Nordic Institute for Theoretical Physics, also known as Nordita. Her talk name is A Century of Astronomical Observations from VASCO or VASCO. Beatrice is an astronomer at Nordita in Stockholm, Sweden. She has a PhD in astronomy from Uppsala Universitet from 2017. Since 2017, she has been running the Vanishing and Appearing Sources during a Century of Observations project, known as VASCO, in search for vanishing stars and anomalous transients, and is now project leader of the newly started EXOPROBE project that will search for extraterrestrial probes near Earth. All right, I'm very happy to introduce Beatriz and go ahead and start your presentation. And thank you very much for being here.
Thank you a lot for inviting me. It's a pleasure to be here. It's the first time I'm joining an SCU conference. So
Yay.
I'm going to talk about how to search for ET probes, both with the VASCO projects and with the EXOPROBE project. So it's two different projects, but one follows the other. So imagine if, instead of waiting for a UAP to appear above your head, you could use a carefully designed instrument to search for UAPs up to 50 million kilometers away from the Earth. What if you could also localize the object and verify its existence in real time? This is the idea of the EXOPROBE project. Let me present it to you. With this project, you don't have to just imagine. Actually, we are a team of professional scientists, mainly astronomers, and we have finished designing an entirely new system that we right now are testing. This new system is planned as a global network of optical telescopes spread around the Earth. We use high-speed cameras that gives us a time resolution, a spatial resolution, and a spectral resolution on any discovery. This permits us to localize an unidentified object in 3D and tell you where it is. Moreover, it also allows us to search for space probes and remains there. So our goal is to detect, to localize, verify, and reproduce the finding in real time, and also getting the spectrum of it directly. For us, the scientific method is central. And if you compare it to other UFO projects, we search for an identifiable signature of the unidentified object. Let's say an exploratory spacecraft from an extraterrestrial civilization, a so-called ET probe. By following this philosophy, we can minimize false positives, and we will not need to vet hundreds of thousands of false candidates that might include flying ducks or any kind of weird airplanes or any kind of unknown objects that humans have launched that are flying through the atmosphere. We want to minimize the human-made contamination. Well, this is just a preview, because I will talk about this more in the second half of my talk, so please stay awake. I will explain then why this system sets the stage for the new generation searches for extraterrestrial intelligence, so-called SETI research. But for that, I first have to tell you about the current stage of SETI, as well as present the scientific findings in photographic plates from the 1950s that have inspired this idea. So let's talk about life in the Milky Way. The two competing teams of Major and Kellos versus Marcy and Butler discovered exoplanets 30 years ago. Many astronomers did not think it would ever be possible to discover a planet around another star than our own. And yet, today we know more than 5,000 exoplanets. And more than 20% of every star that looks like a sun has an Earth-like exoplanet in a habitable zone where fluid water can exist. We can estimate 40 billions of Earths just in our own Milky Way. And also we know that the basic molecules of life can be found on meteorites and asteroids, such as amino acids. And there are all reasons to believe that intelligent life is common. So what is actually the state of searches for intelligent life? Now, people might be differently skeptical or optimistic about it. But so far, we know we don't have any data of the prevalence of intelligent life. So people have been working with radio SETI for a very long time and searching for radio signals. The SETI Institute has been using the Allen Telescope Array, I think, for the last 30 years or so. And the most impressive effort is probably the breakthrough listen that started in 2015, where they have been going through something like, they've been actively looking around tens of thousands of stars and galaxies, but effectively surveyed around 300,000 stars. And so far, even if they have effectively scanned these 300,000 stars, they have found nothing. So 60 years radio SETI has resulted in no viable candidates. Then there are laser searches, and these are fairly new, so they are kind of they have been going on for a couple of years, but certainly not to the same extent as the radio searches have been doing. And I recommend that you look at the papers by Tellis and Marcy, where they have been looking for laser communication around, for example, Alpha Centauri, the galactic plane, and thousands of stars have been surveyed. And this has been done by searching for laser emission in spectra. Nothing has been found so far, although this can still change, given that there's still a lot of searches that can be done. Then there are, of course, the very exotic technosignatures, like let's say, like Dyson spheres. So here one can imagine that you have these giant shells that are absorbing all the light from a star. And in 1991, one did the first searches for these Dyson spheres. And one looked around 545 sun-like stars, and one found nothing. The same thing was done later in 2009. One searched around 11,000 sources. No candidates were found. In 2018, again, the same principle. Nothing was found. So Dyson spheres are still at 0 candidates as well. One can also search for vanishing stars, and this is where the VASCO project enters, which is actually Vanishing Appearing Sources during a Center of Observations project. So with the VASCO project, we are doing a search for an exotic technosignature of stellar engineering, which are vanishing stars, where you could imagine that a very advanced stellar engineer would be able to make a star vanish. And what we can see here was something we first thought could have been a candidate. This is something in the image from the 1950s. You don't see it later in the 80s, and you never see it again, but you see something there. What, however, we learned was that one has to ask a different question. Did the star really vanish? Or did this just represent a very short flash in the image from the 1950s, a so-called transient? Something that briefly flared up and later vanished. Because that is not a star that vanishes. That is something that brightens up momentarily, maybe for a few minutes, few seconds, or maybe for a few days. And this is what we have been doing with the VASCO project. We have been using images from the Palomar survey that was done in the 1950s. And they had a field of view of 6 degrees each side. And they did this huge survey that has been digitized. And we can use these digitized images today and search for things that existed in the 1950s that you cannot find in the latest modern surveys, astronomical surveys today. For example, the Pan-STARRS that started in 2015. And you can simply compare the images from Palomar with the images from Pan-STARRS and see, has something vanished from the Palomar and the images in the 1950s? Just to remind everyone, the first satellite was launched in 1957. So the Palomar images from 1950s are actually from before Sputnik 1. So the VASCO project, as I explained, we have been searching for vanishing stars for a while. We have been using two different methods. First, we have done an automated search, where we have scoured for terabytes of image data, 600 million objects, and we have found thousands of short-lived transients. But so far, we have found no real vanishing star. This result from the automated search was published in monthly notices, and you can find it there. We're also doing a citizen science project. We have so far not found any real vanishing star. We have found some interesting cases that we're looking into and will be looking into this coming day. So in the citizen science project, we have actually developed a web interface where everyone are welcome to join, and they can look for vanishing stars by examining the candidates. And you can directly compare the images from the Palomar with the images from Pan-STARRS. And this is a project that is still being analyzed. So what did we actually learn? We might not have found any vanishing stars as we were hoping for, but we found many mysterious transients that are lasting seconds to minutes. Now that is much more interesting than one may imagine. So let me make a light summary of the SETI approach. This table summarizes all important search efforts in the field of SETI that have been done so far, which, if to be fair, is not much. The radio has not yielded any candidates. We have 60 years of proofs that radio searches don't really work. Lasers are still being searched for, but haven't so far yielded any candidates. But I think that one can expand on these searches much more. Vanished stars, so far they are none, and we have managed to set a very tight upper limit when it comes to in comparison to other technosignature searches by probably sampling the largest sample. We did find something else, however. And this image was actually discovered by chance. So this is an image that, in case you would look at the sky with the same instruments today as the Palomar is using, it would be completely normal to see whatever you're seeing, because you have so much of satellites and space debris that we humans have and caused. The problem with this image is that we are actually watching an image from 1950, 7 years before Sputnik 1. And what you see here are 9 stars in the green circles that appear in an image from the 12th of April 1950, and that never are seen again, and they're also not seen half an hour earlier. So they appear and vanish within half an hour, and they also all have star-like brightness profiles. Now, that is very interesting, because first we examine these images for if there are any kind of way of explaining them with known astrophysics. We know there's asteroids and meteors, for example, that are moving in and out quickly in images. They usually leave streaks, not point sources. We could exclude fragmenting asteroids. We could exclude the idea of that a mere dust cloud was passing in front of the images, because only these 9 stars were affected. We could exclude the typical micro-lensing events and the typical idea of that you have some kind of afterglow from a gamma ray burst or any other type of astrophysical transient. Nothing is consistent with a high number with 9 star-like images that appear and vanish within half an hour in this small image box that we have. We're wondering, maybe it's a new phenomenon. We started looking into various kind of instrumental issues. Could it have been different spectral sensitivity of the images? No, because we could compare 2 identical red Kodak images at the same emulsions with a few days in between, and the stars were there in one of them but not in the other. We could exclude ghost images. Double exposures couldn't be excluded entirely, but they seemed very unlikely based on the test that we were doing. Emulsion problems some people say, but it also doesn't seem too likely, given that all of them are having very star-like brightness profiles. And the same goes with the cosmic rays, because also remember that cosmic rays are a problem for CCDs. But it's also not impossible, but just not too likely. Could somebody have sneezed, asked our referee. Now remember, we actually submitted this paper to a journal during COVID, and we didn't think ourselves about the sneezing, but our referee thought about that we should have thought about the sneezing, given how many people were sneezing during the COVID. And we could exclude that too, because it didn't, the sizes of these spots did not match what you expect from saliva. So we eventually land in two types of explanations. And one possibility is that you have nuclear fallout that produce false stars, some kind of plate defects in such a case, that cause false stars on the photographic plates. And you see here an X-ray images with such false stars, and we don't know if these red emulsion images could be affected the same way. And the only problem is that our images are from 1950, and in that year there were no official atomic bomb tests in the United States. Tough luck. So explanation 2 that we were thinking about is that possibly we could see some kind of reflections, solar reflections, some flashes from artificial objects in high orbit around the Earth, like you see here. Because if you have small objects, even just centimeter or a decimeter size at a certain altitude, you can produce actually very short sub-second spectral reflections. And you could also have actually flashes coming from direct light emission if you have some objects emitting actively. And this is something we were wondering about. It's just that, again, our image is from 1950 when there was nothing up there, nothing human. So the nice thing with photographic plate searches is that photographic plate searches are less sensitive than CCDs to things like we mentioned the cosmic rays. The pre-satellite sky was just pristine. As far as we know, I'm at least not aware of any secret human rocket launches in the early 1930s to those altitudes. But these photographic plate searches are also ideal for solar system SETI, with the only problem that the long exposures, usually 50 minutes, leads to a flux dilution. So what kind of predictive signatures of satellites and space debris do you have if you search for them in photographic plates? Well, multiple transients. If you have a rotating dish, you can also expect to see a triple transient like here. You may expect to see several transients along a line, not necessarily as perfect as in this image. You can also just see a few, and it doesn't have to be periodic either, as you can have all kind of complex shapes and sizes and geometries. So how many simultaneous transients along a line do we need if we would like to separate between the two cases of multiple transients, where you have multiple transients just by chance because you have some very, very unusual plate defects or so that just landed randomly? Or if you actually want to look at those specifically that fall along a line, so that you get some candidate. So if you look in a small box of, let's say, 10 arc-minute size, you can estimate by statistics that you would need at least 4. Now, if you have 4 transients along a line, it has fairly good chance to come from a satellite rather than be some kind of plate defects with very unlikely but very beautiful shapes, or coincidentally beautiful shapes. That's what we estimated. So one way to search for candidates of ET probes is therefore to look for this, for at least 4 transients along a line. I know what all of you are thinking. Do you see any such? Well, here we have a paper that is called the paper that's getting a lot of very hard time in review. And here we see actually 6 transients that appear and vanish within one plate exposure. And 4 of them are very beautifully aligned. You can see here the probability. You can do some statistics, use the statistics from developed by Michael Edmonds, and you get how likely or this alignment is. This is a even more beautiful case, in my opinion, that happened on the 28th of July 1952. And these 2 cases are our top cases, or the best 2 cases that we have found when we have been looking for aligned transients. I'm pretty sure that some of you are going to recognize these dates. Now, if you look at the probability, we're getting to a very small probability for this alignment. So the funny part about this was when we put the paper on archive, I got an email from an astronomer who sent me like a note writing like, didn't you think about that this is just satellites you're watching? And this started up a very fun email conversation because the astronomer had forgotten that in 1952 there were no satellites in the sky. And well, I could continue telling the rest of the conversation, but I'm afraid I will lose the time for the rest of the talk. So what are the actual implications of what I'm telling you? Well, let me summarize it for you. There are unexplainable multiple transients in all images from 1950. They look exactly like stars or normal transients, and they do not appear to be plate events. They appear and vanish within seconds or within minutes. Some of them are even aligned. And they are so rare that you will not find them today unless you do dedicated searches. For fun, we have also estimated the density. And we have simulated possible shapes in case they are caused by solar reflections, as you can see here in the image on the right. 5 examples of shapes that can produce this. In case all these multiple transients turn out to be false, the VASCO team has estimated the first upper limit of the surface number density of ET probes near the Earth. And this is the first survey that ever has been done. And here we have the potential number density in case our 2 top candidates are totally wrong. But this also asks us to actually do these searches in modern surveys and do these searches with modern instrumentation to try to see, can these multiple transients be found today? And what is causing these multiple transients in case they are real? And to be able to validate and verify this kind of discovery. And especially if they come from ET probes, then it's this time for us to ask, can we catch ET? So, in order to do that, we are going to actually join efforts. So, first we have the VASCO team. The VASCO team publishes every year something in peer-reviewed journals, both new methods and scientific results. Our team, an international team, is, as I mentioned earlier, is the first out finalizing a pilot survey for ET probes around the Earth, which we did with these searches in the photographic plate surveys. And now we are teaming up with Space Laser Awareness that have many publications every year. They have a new detection technology, and they are really, really good at searching for lasers. And they also produce actually new papers every year, and they have lots of scientific results. And the point is that now we're joining forces. So here we are going to actually introduce to you the EXOPROBE 2023 to 2026 plan, where the principle is to use this global network of wide field telescopes. The advantage of this is that we can have verifiable, reproducible searches, and we can have a minimal number of false positives. And the goal is to do it so accurately, to localize it so accurately, that you can, in principle, go and fetch the object, the alien object, and bring it down to the Earth. We actually already have purchased the instrumentation, and we're going to use a plane wave delta rho telescope, the state of the art of this kind of telescopes. And we'll also use CMOS cameras with short exposures to search for ET. And we're starting small scale, of course, and we're going to later expand to a complete network, but we start very small scale. And so what is the current stage? Well, regarding the design and research plan, it's proprietary still. And if you want to ask me more about it, please speak to me one-on-one. We are working with a telescope prototype still, and we are waiting for the new instrumentation to arrive. And we're also testing the methods that we are developing with pre-existing astronomical data. It's very interesting to see what other telescopes might have found if you use similar techniques and filtering methods that we have. So when is the official project starting date of EXOPROBE? It starts actually on Tuesday, the 1st of August, 2023. Yes, I think it is in 2 days, because today is Sunday, if I remember correctly. And we are also funded, and we are very grateful to Anomalous donor. So let's have a look at this network of telescopes. So by now we have tested the prototypes that we're going to use of this global network, and these telescopes are going to be equipped with these special high-speed cameras and spectrometers. The unknown objects are identified and verified in real time. We will also have special optics that gives us this 3D position and the spectra, and with the filtering system we will eliminate confusion with human-made satellites or space debris. And anything that flashes or glints will be found. You can see here we are going to be using wide field spectroscopy, and here I show you a 0.25 second exposure. We have here novel optics that yield spectra of unidentified objects in real time. This test exposure shows the Pleiades. And you can see here like dozens of spectral stars that appear. And similarly, if you have an unidentified object, you will get the spectrum directly. Let's have a look here at this unidentified object, how it looks if you see it in this spectra. We have here 7 frames, and you see how it moves through the field of view. And this diagonal line is something with a very, very narrow emission, like a laser line. And by doing this and like using this instrumentation, you can actually get the detection, the validation, and the spectra in real time of our UAP, or our unidentified objects outside the Earth's atmosphere. And of course, if you have the spectra, you can get a chemical analysis, and you will be able to see if the spectrum is solar, like in reflected light, or if it looks somehow differently in any way. So you'll get simply the chemical composition of the object or the light source. And the beautiful thing about this is that we can also search for lurking probes and UAPs that also are hiding on asteroids, because there are many theories developed, in particular by John Gertz and by Jim Benford, where one hopes to find let's say a Bracewell probe that has been sent to and put on an asteroid. And this project we have co-developed with Dr. Geoffrey Marcy, who is also main responsible for the project design and for developing the methodology of the EXOPROBE. I think he's also in the audience in case you have questions, technical questions about this. So Dr. Marcy is a pioneer within exoplanets, and he is the discoverer of the first 70 out of 100 exoplanets. He discovered the first planetary system around a sun-like star. And for this, he has received lots of very, very, very important prizes for it. For example, the Shaw Prize in 2005, which is the Asian version of the Nobel Prize. And also the NASA Medal of Exceptional Scientific Achievement and the Carl Sagan Award. is also the creator of the Breakthrough List and $100 million program. And now we are working on the EXOPROBE. So I have good trust in that we're going to get interesting results soon. We're also working together with Dr. Brian Hill at Deep Springs College and John Gertz. We're also collaborating with members from the VASCO team. That's many of you have seen this image where they're mostly astronomers and some machine learning scientists. And the VASCO team had a meeting in December where we were roughly 50 participants. It was a hybrid meeting at Nordita at Stockholm University. And if you want to see the publications, please go to our webpage. And I'm going to leave you with this animation showing how this global network of telescopes can look when we reach that stage, placing multiple of these telescopes, and when an object is glinting here, and how it can be caught. And I hope you enjoyed the animation, and I thank you all for attending my talk and the opportunities to speak here. Thank you.
All right, great. Thank you very much for the presentation. Very exciting project. Remember, if you have questions, please submit those to the Q&A section in the session. There are a couple here. One person would like it if you could expand on the flashes that are sometimes being aligned.
So we have been searching for kind of alignments. Because imagine you have this object and it's rotating, and sometimes you're going to have the metallic surface or the very reflective surface is going to reflect the sun, and sometimes you're going to have the non-reflective surface hitting the sunlight. But when you get this reflective surface producing this glint, you will be able to simply see it from here on the Earth. And you're going to see maybe multiple of these as the object is moving. And the point is that you can simply use this as a kind of statistic. The problem we have been facing is that, let's say you see multiple objects, and you're wondering, like, these multiple objects or multiple stars, can it be so that there's some kind of very unusual type of plate defect that produces something that it looks exactly like a star, even if it's very coincidental? We don't know of anything like that, but let's assume for a moment there exists something that really produces this kind of very star-like contamination. How would you separate that situation from a situation where something is there and glinting? Well, it's by the movement of the object, and that you simply want, and that it's going to produce these flashes as it tumbles. And then you can look for these alignments. And that's the point of looking for these alignments, trying to separate the two situations, the hypothetical plate defect situation from a hypothetical situation where you have the object being tumbling and sometimes reflecting lights.
Gotcha. And then this next one is more of a comment, and I think you addressed this, but I'll share the comment with you to see if you want to expound at all. But this person says Marietta Blau's dark stars were cosmic rays detected on photographic plates. Not sure if you have a comment.
Yes, one can be looking for. I mean, cosmic rays could also be detected on photographic plates, but I believe these emulsions are. They were lying there for years, and now if you would have these emulsions, that were so sensitive to cosmic rays, then as they were lying there for years, they would be completely covered. So these astronomical plates must be much less sensitive than any kind of other type of emulsion, because otherwise you wouldn't be able to separate the stars from these kind of cosmic rays. And moreover, you can use the brightness profiles, because stars usually, or objects outside the atmosphere, are going to have a certain type of brightness profile that allows you to separate it from any kind of cosmic ray or defect or anything like that. And that is how we have been working, by looking at these brightness profiles, for example.
Gotcha. And let's see. Are you saying that there are alien probes in orbit around the Earth? And if so, why haven't we detected them with all of our new telescopes since 1957? With all the satellites we've launched, wouldn't we have seen them? I think they're misinterpreting what you're saying, but maybe you could clarify.
What I'm saying is that we can search for alien probes because there are methods to do it. And but if we assume that these glints that we see in the VASCO project come from alien probes, we would not be seeing it with all the objects we would not see it just so easily because we have so much of satellite contamination. You have 1 million of pieces just larger than 10 centimeters in geosynchronous orbits around the Earth. And with and that produces like thousands of glints over the sky every hour. And now to find something that only happens once per day or once every few hours on the sky, you're not going to see it just like that. So no, we wouldn't see these alien probes unless we actually search for them. And that's because we humans have contaminated our sky so much.
Mm-hmm. And with the objects you're detecting, I guess distances could probably vary greatly.
Yes, and that's why we are going to be focusing on localizing things.
All right, let's see. In looking for transients today, how are you dealing with the issue of various secret satellites potentially corrupting your data?
Oh, we will discover that. We have several ideas on how to separate the issues. And I guess one way that also might happen is that if one of us gets a knock on the door, we will know. So, but we are working on filtering methods for that too. I can't too carefully.
Okay. Makes sense. Still in process. Have you been able to exclude the broken arrow incident of February 14th, 1950 as a potential cause for the lights on the April 1950 plates?
Broken arrow incident? I'm not familiar with it.
Broken arrow typically means a lost nuclear device.
Okay.
So I'm not...
Okay. Oh, sorry. Yes, I already forgot my basic. So can you repeat the question once more?
Yeah, no problem. It's have you been able to exclude the broken arrow incident of February 14th, 1950 as a potential cause for the lights on the April 1950 plates?
We have been looking at that, and if you look into our paper, we have a supplementary information where we discuss why we think it is unlikely, even if we don't exclude it completely. It's not impossible, but we find it rather unlikely, and I recommend that you look into our supplementary information section in the paper describing the 12th of April 1950 plate.
What was the most recent findings that eliminated the remainder of the vanishing star candidates? The last time I heard one of your fascinating presentations, I believe there were 1,100 candidates that were examined.
Yes, now I remember. Those, yes, because these ones turn out to be, we have been imagining, we have been, not imagining, we have been looking at the images, apologies, for one by one of all these candidates. And the way how we can do that is that when you have these 1,100 candidates, you can see if it's seen in more than one image or if it's seen in multiple images. If you have something that is a vanishing star, you're going to see it in multiple images before it vanishes. Now, if it turns out to be a transient, something or a very short-lived transient, you're just going to see it in one image and never again. And by doing this very meticulous effort of comparing or looking at the candidates individually, our team, VASCO team, has been vetting them one by one and simply excluded almost all. We still have a few left that we are looking at a little bit extra.
Gotcha. Great. Thank you. The next question, Are you aware of the recent paper by the Kiev, Ukraine astronomy group claiming to detect complex flashing glint patterns emitted by UAP they named blinkers? If so, does that pattern fit your model for a tumbling natural object?
I'm not familiar with the blinkers that they have been discussing, because last time I saw it was the cosmics and I forgot the other name they call them. Ghost. They had two classes in their first paper.
Cosmics and phantoms.
Yeah, cosmics and phantoms. And then I haven't seen their latest papers. So I will be glad to have a look into it.
I'll post a link.
Great. Great. Thanks for the added info. All right. Is that the remainder of the questions? All right. That looks like all of the questions so far. So thank you very much for your presentation. I think that it's a very exciting project that many of us are looking forward to the results and are definitely supporting your effort. And thank you very much for presenting.
Thank you.